I'm Connie Senior from ADA-ES. We make equipment for sorbent injection for mercury control and acid gas control, as well as for oxidation control of mercury. And I'm going to start off our mercury sessions just to provide some background on mercury forms in combustion systems and the importance of oxidation. And hopefully, at least by the end of the talk, you'll understand about the importance of oxidation. So I want to talk about the forms of mercury in process gases and its origins, the measurement of different forms, and ways to oxidize mercury. And when we talk about mercury in combustion flue gas, and that means combustion gases from cement kilns, incinerators, coal-fired boilers, coal-fired power plants, mercury is a little different from some of the major pollutants that are measured in those systems because for the most part you only have to worry about one form of a given pollutant. For NOx, it's mostly NO, especially in coal combustion systems. For SO2, it's mostly SO2. But for mercury, the form of mercury in the flue gas can really vary depending on a lot of conditions. And that affects how easy it is to remove mercury from the flue gas and control the emissions. And so that's why it's important to understand the forms of mercury in flue gas. So mercury emissions are regulated from various combustion sources, as I mentioned. Mercury is present in the fuel or in the raw materials in some cases, and it can end up in the combustion exhaust gas. So in Portland cement kilns, for example, there's mercury in the limestone raw material as well as in the coal-fired boilers. There's mercury in the coal. Incinerators, mercury can be in the waste. So mercury comes in various forms in these systems, but it's very volatile, so it will all end up in the combustion gas in the high temperature zone. As I said at the outset, unlike other major pollutants from combustion systems, mercury is found in several forms in the flue gas. Different forms of mercury interact differently with air pollution control devices. And that's why it's important to spend a little time talking about the forms of mercury. Different forms of mercury have different impacts on the environment once they're emitted, which is also, there's another reason why it's important to understand the forms of mercury that are coming out of the stack. The forms of mercury are defined really by the available measurement technology. So we have gas phase mercury. It can either be elemental or in an oxidized form. That could be, a common one might be mercuric chloride, for example, in coal combustion systems. We don't really have measurement methods that are commonly used in industrial combustion systems that can tell us more than just the mercury is elemental or the mercury is oxidized. And then there can be particulate mercury, which is mercury that's adsorbed on particles. So just a little bit about mercury chemistry in flue gas. In the combustion zone, all the mercury is elemental. It's released in the high temperature of the flame as an elemental gas. It can undergo gas phase reactions in the combustion system that can through gas phase chemistry, oxidize it to something like mercuric chloride. It can undergo heterogeneous reactions, so it can react on particles in the gas. It can be adsorbed. It can be oxidized catalytically on those particles. And so we end up with our three forms of mercury: elemental, oxidized, and particulate, as the flue gases leave the boiler or the high temperature zone and enter the air pollution control equipment. Just briefly to talk about measurements, because if you're trying to understand how much oxidized mercury is present in the process gas, you have to figure out how to measure that. If you're just concerned about stack emissions, those are written in terms of the total amount of mercury emitted. So then you don't have to worry about the forms of mercury in the flue gas if you're just thinking from a regulatory point of view about the emissions. However, if you're trying to understand how a given piece of air pollution control equipment will impact mercury emissions, then sometimes you have to do some homework on the measurement to actually measure the forms to understand that. There are batch methods for measuring mercury. There's a number of wet impinger-based methods, including the Ontario Hydro method, method 29 as well. And then there are dry batch methods, sorbent trap methods, we call them. The Ontario Hydro method has a probe and a heated filter and a whole bunch of impingers that contain solutions that are designed to resolve the species of mercury. Method 29, which is used to measure total metals in stacks, does not speciate mercury adequately. Dry batch methods can be adapted to speciate mercury. I don't know if you can see down at the bottom, but this is a sorbent trap at the bottom of my slide that has different media, solid media, that are used to collect first oxidized mercury and then elemental mercury. There are also continuous emission monitors for mercury that speciate mercury into either elemental forms or oxidized forms. These only measure gaseous mercury, obviously. They can only measure or detect elemental mercury. So similar to a NOx analyzer, if you want to measure total mercury, you have to convert all the oxidized forms to elemental mercury, usually using a reagent or some kind of catalytic process. And again, these don't measure the particulate component. So there are two ways to remove mercury from combustion systems, and the next two speakers will talk about those methods in detail. But one is to adsorb mercury on particles. That could be particles in fly ash that comes from the combustion process, particularly the residual carbon in the fly ash. Sorbent injection, so there are targeted sorbents that will adsorb mercury, or fixed adsorption structures. You can absorb oxidized mercury into wet flue gas desulfurization systems, dry flue gas desulfurization systems. So why is it important to increase the amount of oxidized mercury in the flue gas? Many coal combustion plants and some industrial boilers and very few cement kilns have desulfurization systems to remove SO2. So many plants could take advantage of those desulfurization systems to also remove mercury if there's enough oxidized mercury present. And this is an example of some data from full-scale coal-fired power plants showing on the x-axis the fraction of oxidized mercury at the inlet to the scrubber and the removal of total mercury across the scrubber for wet desulfurization systems and dry desulfurization systems, followed by fabric filters. So you can see that there's generally a good correlation between how much oxidized mercury you have in the flue gas coming into the scrubber and how much mercury is removed across the scrubber. And there's some reasons for the differences between wet and dry systems that I won't go into here. But if you are regulated for mercury emissions and you have to achieve on the order of 80 to 90% mercury capture, you may be able to do that with your flue gas desulfurization system. However, you have to maintain a very high level of oxidized mercury coming into that device. Mercury can react with halogens in the flue gas. It loves to react with halogens. Halogens can be present in the fuel, or they can be added. They can be added just as adding halogen compounds to the fuel, or you can also add halogenated sorbents to the flue gas. So that's a way of increasing the amount of oxidized mercury in the flue gas. This shows an example of just the mercury that's native to the fuel. The x-axis shows the chlorine content of coal, and this shows the sum of oxidized mercury and particulate-bound mercury at the inlet to the particulate control device. And these are all data from coal-fired power plants. These are actually from the 1999 ICR. And so you can see as the amount of chlorine that's just native to the coal goes up, the amount of either oxidized mercury or particulate-bound mercury goes up as well. There's a lot of scatter in these data, but the temperature in the flue gas, the amount of unburned carbon in the flue gas, whether or not there's an SCR upstream, all affects that. But for coals that have a lot of chlorine, for example, and that's mostly eastern bituminous coals in the US, there tends to be a lot of oxidized mercury and the potential for good capture in existing devices. So you can increase the amount of oxidized mercury if a plant has an SCR. A lot of coal-fired power plants have SCRs, not really that many industrial boilers or cement kilns. There's a couple of factors that are important for that. Now, as we heard earlier, SCRs are used to reduce NOx to NO2, but the catalyst can also oxidize elemental mercury. One of the factors is the effect of chlorine. In order to oxidize mercury in an SCR, you have to have some halogen in the flue gas. Again, this is full-scale data showing the coal chlorine content on the x-axis and how much mercury was oxidized across the SCR. So as we increase the chlorine content, the amount of oxidation goes up. Again, there's quite a lot of scatter, which the factors that are important are temperature, which I'll illustrate in a minute, as well as the design of the SCR catalyst, the composition of the catalyst, and how much ammonia is being used. And then temperature in the SCR is also important. This shows a temperature on the x-axis, and again, the amount of mercury that was oxidized across the SCR. Here, as the temperature goes down, the amount of mercury that's oxidized goes up. This kind of goes counter to what's happening for NOx, because in SCRs, as the temperature goes up, NOx destruction efficiency goes up, but it's the opposite with mercury. And so one thing to note for people who are operating power plants, sometimes, for example, in the winter, or when the load is low and you don't need as much power, you may operate your SCR at lower temperatures, but as the demand for power goes up, you may operate at higher loads, which increases the temperature in the SCR, which would tend to drive down the amount of mercury that's oxidized across the SCR. So a lot of times people say, well, I'm just going to put on an SCR and a wet scrubber and I'm all set for mercury control in my plant. Well, that's true, but you do have to pay attention to how those devices are operated in order to get the most out of them. You can also add additional halogens to the fuel, and this shows some information from some studies on Powder River Basin subbituminous coal-fired boilers. Powder River Basin coal is very, very low in chlorine and tends not to have a lot of oxidized mercury. But in this case, experiments were done to add a lot of different halogen compounds to the fuel, or to the flue gas in some cases, to see how much oxidized mercury that could be produced. And the y-axis shows the fraction of oxidized mercury at the inlet to the particulate control device in these cases. And the x-axis shows the equivalent halogen content that was added in parts per million. So for all of these chlorine compounds, as we increase the chlorine that we put in the fuel, we get about the same increase in oxidation no matter what we start with. And we've seen that from looking at just coals with different chlorine contents. I would note that when people tried adding bromine, we really don't need, the observation is very much bromine to be added to very effectively oxidize mercury. So while all mercury interacts with all the halogens, it's more effective, at least on a weight for weight basis, with certain halogens. This is another example of addition of bromine to the fuel with a boiler that has an SCR, and the speciation of mercury, in this case the concentration of elemental mercury in the flue gas, was measured at the inlet to the SCR and at the outlet to the SCR as a function of the amount of bromine that was added to the coal. So we're driving down, as we're adding bromine, we're driving down the amount of elemental mercury, both at the inlet and the outlet to the SCR, to produce more oxidized mercury. Recently, a number of catalyst manufacturers have found ways to redesign SCR catalysts to make them more effective for mercury oxidation. And I show just some information from Hitachi, which is now Mitsubishi Hitachi, and from Cormatec, looking at some of the developments that they've been working on. So as with anything in our industry, when there's a need that comes up, a lot of smart people can start looking at it and try to figure out how to fix that. So we'd like, if you're going to use an SCR catalyst, which is not a mercury oxidation catalyst, it's a NOx catalyst for mercury oxidation, then paying some attention to its operation and how well it oxidizes mercury is very critical. So just to summarize, unlike a lot of the major pollutants like NOx and SO2, the forms of mercury are really important to how effectively that can be removed from the combustion flue gas by air pollution control devices. Increasing the amount of oxidized mercury in the flue gas can be accomplished by adding halogens to the fuel, adding halogens to the flue gas, by using an SCR catalyst, especially one optimized for mercury oxidation. And that's all I have. Are there any questions? And I would say our next two speakers are going to go into some of these aspects in a lot more detail. So, yes. The question is, when you add bromine, is there an increase in HBr? Yes, there is. There may be some Br2 as well, but method 26 does not speciate bromine correctly in coal combustion flue gas. But certainly there have been a number of measurements of HBr as a function of putting bromine into the fuel. And you can measure HBr with FTIRs as well. Any other questions? All right, thank you.